All right, welcome back, everybody. Thanks for coming back from the break. Once again, my name is Jim Way. I'm Executive Director of this here American Astronautical Society. You can find out more about us at astronautical.org. Let's get right into our next session. Our next session is Novel Concepts and Advances for Space Operations. This one should be really cool. Our session chair for this segment is George Freas. George is the owner of Freas Consulting, LLC. This segment includes 5 presentations. We're taking a look at them now. We've got some really cool stuff. Virtual reality, ground-based monitoring, RFID logistics management, robotic surveying, and attitude control for the Astrobee robots. That should be pretty cool. They have to have their attitudes adjusted. So without further ado, let's get into it with the first of our presentations.
Good afternoon, everybody. My name is John Williamson. My contact information is down below. I currently work at SAIC, and the title of my presentation is Virtual Reality Updates to ISS EVA Mission Control. One of the things that makes this presentation interesting is that it's actually a sequel to a talk I gave 2 years ago called The Past, Present, and Future of VR in Space Exploration. I need to apologize up front. I am no rocket surgeon. I am a game designer, so some of the terminology and slang that I'm going to use is probably not correct, so I apologize in advance. I have shipped about 3 dozen titles on 15 platforms over the years. I have used just about every virtual reality headset that's been on the market in the last 30 years. And currently my biggest project is called Pilot Training Next, and it's using a slew of virtual reality and game applications to help train our U.S. Air Force pilots faster. A big part of my talk last year was on the future of AR and VR, so I just want to cover a couple of those again. One was for exercise, so using virtual reality as a way to help give you something else to look at besides the walls of the space station, as well as provide some competition and gamification, either virtual or against other astronauts or against maybe people on Earth. Using holograms, in this case from Microsoft's HoloLens, as a way to keep astronauts in touch emotionally with their family members back home to provide a more realistic experience. And then also this could be used to provide updated training in 3D as well. Also using virtual reality for post-traumatic stress disorder. If there's an accident in space, we'll need to get our astronauts back and working again. It's a long way home. The same thing for pain reduction if there was an accident. Just using simple distraction techniques using virtual reality has been shown to significantly reduce the amount of opioids required to get through painful procedures. And this is demonstrated not just in how many opioids the patients request, but actually in MRI scans show a difference as well. But as an outsider, the thing that stuck out to me the most was the fact that it looks like not much has changed in mission control in the last 60 years. So we've moved from black and white CRTs to full color flat panel LEDs, but there's still a lot of 3-dimensional information that's scattered and being displayed occasionally in 2 dimensions. And so the idea was that we could use the cameras mounted on the space station to triangulate where the astronauts are using a process called photogrammetry. And then we could take those disparate 2D displays and actually put them here in situ. And so using the Unreal game engine, we were able to make a prototype in about a day. You can see the astronaut down below, some notional camera feeds and vital signs, a green waypoint path showing where they're supposed to be and what time they're supposed to be to get there. In this case, they're behind schedule. And with that, I was able to get some research funds from SAIC to create a more advanced prototype. And here I can click on an astronaut and then see their vital signs displayed up above them. There's an astronaut who tried to escape, but we're bringing them back down. I can click on a different astronaut and see their mission objectives, how they're supposed to accomplish the task, and then a live video feed, again in situ. I can also see their waypoints, where they're supposed to be, if they're ahead or behind schedule, and the tools that they need once they get there. And this time we decided actually to make it more life-size as opposed to a dollhouse feel. The other interesting thing about this design is we can use it for just about anything where there's a lot of two-dimensional displays trying to describe a large three-dimensional space, whether it is a launch complex or in this case an oil refinery. And again, I could click on the information desired and then see it there actually in the three-dimensional space where it is, which should help me understand the problem a little bit better as well as try to find the solution. And then I can also go down and see it instead of doll's house view, I can go down and see it in human scale. And again, there's my contact information down below. I'd love to hear from you if you have any questions. Thank you.
Hello, my name is John Kichury. I'm a software developer on the Spaceborne computer team at Hewlett Packard Enterprise. In collaboration with NASA, our team designed, built, and deployed an HPC or high-performance computing system on the International Space Station. The purpose of these missions is to determine if off-the-shelf standard HPC systems can operate in space and provide computing power in close proximity to where it's needed. Such capabilities will help mitigate the latencies and reduce network bandwidth associated with remotely using Earth-based systems. This is an executive summary of the status reporting and dashboard mechanism I had developed for this project, and on which I will be delivering an oral presentation for the ISSR&D conference. Using a custom-written software stack for autonomous operation aboard the ISS, the status reporting and dashboard mechanism provides monitoring from our ground station. In the oral presentation, I discussed the purpose of the mission, main design features of the software, and the architecture and data flow between the various components. I also discussed the ability for the dashboard to display near real-time data, cover the level of detail we're able to achieve on a single screen for visualizing the health and status of the systems and the experiments being conducted, including error and alert conditions. Also discussed is a custom track viewer for displaying the ISS location and ground tracks. I present the track viewer's ability to display dangerous window regions such as the South Atlantic anomaly intersections and the ability to plot system anomalies for correlating with known conditions in space. Finally, I discussed the various types of data queries and reporting useful for assessing the system's health and for performing analysis should an anomaly arise. The goal of this project is to perform experiments for providing high-performance computing resources and advancing the science in space. Thank you for joining me.
Hello, my name is Patrick Fink. This presentation is Advances in the International Space Station Realm, RFID-Enabled Autonomous Logistics Management. Our experiences on the International Space Station have helped us to fully realize the complexities in maintaining and managing a large inventory that is required to sustain life and conduct experiments in a remote environment. And while future deep space missions may not entail the large amount of cargo that is seen on the International Space Station, the penalty for losing an item or not being able to locate the proper item in a timely manner may be much more severe. There are several key differences in operating an RFID system in a space habitat. Not the least of these is the complex RF scattering environment that is induced by the metallic shell of the vehicle. And so instead of clear plane waves that we get in open environments or in high bay environments terrestrially, we see very complex peaks and knolls in the field patterns across the vehicle. So to add to the complexities of the severe multipath and RF reflections in this environment, we also get cargo that is stacked several layers deep and tends to limit penetration to tags that are buried, as well as metal racks that preclude RF penetration to tags inside of the rack. And then in addition to this, we're levying requirements for much finer localization accuracy than is typically requested for terrestrial RFID deployments. We need to get our crew into a specific rack in a 1 cubic meter volume in order to get their hands on the items they need in a timely manner. So at the core of the realm experiments are 3 building blocks that were intended to overcome these challenges and limitations with RFID technology. And the overarching goal of the realm experiments is to determine the optimal set or use of any of these 3 technologies in future missions. The first is a fixed reader fixed antenna system known as Realm 1. The second is a robotic free flyer equipped with RFID readers and antennas. And the third is a smart stowage system in which the signal from the reader is fed into stowage racks directly, enabling deep penetration of dense collections of tagged items. In the full presentation, I'll review the overall progress in the realm experiments, and in particular, the advances in the Realm 1 localization capability. We find machine learning advances greatly improve upon more traditional algorithms for localization. And most surprising to us is the ability of these algorithms to localize RFID tagged assets in non-instrumented modules. I will also touch upon the Realm 2 and Realm 3 technologies that are nearing activation. Thank you.
Hi, I'm Ian. I'm a PhD student at the University of Pennsylvania, advised by Vijay Kumar. This work is also done in collaboration with Trey Smith at the Ames Intelligent Robotics Group through a NASA Space Technology Research Fellowship. So I think it's fairly intuitive that situational awareness is useful for robots. Robots need to know what their environment looks like and what their system state looks like in order to be able to make intelligent decisions. So in this work, we're interested in the problem of deciding what a robot should do, in this case, the Astrobee free-flying robot on the ISS, in order to gather useful information about its surroundings. More formally, we want to fly trajectories that will provide data to generate a high-resolution colorized 3D map. And we can think about this in some sense as texturing a mesh. So if we have some loose prior on what the geometry of a module looks like, this is the gem on the ISS, we'd like to colorize it and maybe also refine the geometry. But we assume that the existence of an algorithm to do that. We just want to pick a trajectory that will give us the data to do this as well. So our pipeline begins by simplifying our prior mesh. This is done so that we get rid of any loops or holes and make sure it's one contiguous unit and there's no extraneous geometric information there. So we simplify the geometry, then we run it through our planning pipeline, which was the main focus of this work. And finally, the output of our algorithm is a sequence of poses, which the local Astrobee flight software can then fly between to execute the path. So given that we kind of know in advance what the geometry is that we'd like to survey, our goal is really to fly a path such that we see with our camera the surface area of that mesh. And we can think about this as kind of a projection onto a plane. So if we have some piece of a mesh, like in this case, a semicircle or semisphere, we can project that onto what I'll call a chart with orthographically, and this forms a one-to-one mapping between a 2D texture and this 3D mesh. But the problem is that if the mesh is closed, like it's a sphere, for instance, then this mapping is no longer one-to-one. So we need to decompose the sphere into a bunch of smaller meshes, such as these, which we can then individually project onto their own planes. So if we have this small mesh like so, and we project it onto the chart, then we can effectively use well-known surveying techniques in chart space, such as bastrophodon planning, which is just basically a zigzag path on the chart. We can sample survey points along that path and then project those back onto the mesh. And there's also a normal vector that's associated with the chart plane, and we can use that to then stand off our survey pose by some survey standoff distance to come up with a three-dimensional pose. And these poses still have an order that's imposed by the bastrophodon path on the chart. So now we have our sequence of poses in 3 space. We can refine these poses to avoid collisions, and we're done. So this is what the output of our algorithm looks like. The little red arrows are each poses. The blue line shows the ordering between them. And the bottom shows the survey quality. So the lighter the green, the higher resolution the quality of the imagery is of that particular surface. And you see we do well, except for around the airlock in the gem, which makes sense because in order to get nice images of these areas, the robot has to be up into this confined space where it can't get. So it has to look at this area more obliquely. So here we have the Astrobee robot in gazebo running one of our survey trajectories. And you can see that it's effectively executing this zigzag pattern. In this case, it's along the bottom plane. And once it finishes that plane, then it would move on to surveying the sides and the ceiling. And so this sort of a trajectory that results from our method is very similar to likely what a human would design, which is very intuitively satisfying. So with all that said, happy to take any questions you may have. My email is here. Thank you for your attention.
My name is Dario Ruggiero, and today I'm going to introduce this research about robust attitude control for NASA Astrobee robots operating in the air. First of all, the NASA Astrobee project consists in the realization of 3 high-capable robots able to operate autonomously inside the ISS environment. They are equipped with a fan-based propulsion system, a visual-based navigation system, and a dock station to recharge batteries, and a perching arm for handrail and object gripping. This research aims to realize the Astrobee model in order to couple the attitude dynamics with the manipulator motion, and to improve the existing attitude controller by using a robust controller to overcome the disturbances introduced by the manipulator motion itself. The dynamics model can be expressed from the angular momentum conservation that can be rewritten in the following equation, where the disturbances introduced by the manipulator motion are identified in the overall inertia changing at gyroscopic torque and the torque needed for the manipulator motion. On the other hand, the manipulator has been modeled by 2 links, 2 joints, robotic arm, and its dynamics is fully expressed by the joint's rotation in function of the applied torque in each joint. To control the overall system, 2 controllers are needed. The first one to provide arm motion, and the second one to handle the attitude control and stabilization. For the arm motion, a first-order sliding mode controller has been implemented for its property of low complexity and low computational cost, while for the attitude control, 2 robust strategies have been proposed. A twisting sliding mode controller that has the same property of the first sliding mode controller, but is more precise, and a backstepping controller that consists in an adaptive controller based on the up-node functions. These graphs show the simulation results in terms of LR angles for a manipulator motion that consists in deploying the arm, 2 rotations, one deployed and another in the vertical position, and the final stalling. Both the controllers are able to restore the Astrobee attitude, but the backstepping controller is faster thanks to its adaptive feature. In fact, as the command torque reports, the twisting sliding mode torque is limited with the constant values that define its control law, while the backstepping controller can request an higher torque to stabilize faster the manipulator disturbances. The NASA Astrobee simulator has been used to test the design controller in a more real scenario. It is an open source software realized in ROS gazebo environment that simulate the Astrobee flight inside the microgravity environment of the ISS. Combined simulation between Simulink and ROS have been executed to test the controllers in the physical environment realized in ROS. For the twisting sliding mode controller, the results in terms of animation and error angles confirm the results obtained with the numerical model, despite some errors due to synchronization errors. In fact, due to the high computational cost of the combined simulation, there are some synchronization errors between Simulink and ROS. This problem is more evident with the backstepping controller, where the errors are 10 times higher than expected due to the Simulink delay in the application of torques, like the controller is not working or working with a lower frequency. These effects are more evident in the common torque plots, where the time delay leads to oscillation and unexpected peaks. In conclusion, the twisting sliding mode controller and the backstepping controller are both a suitable solution for the manipulator motion stabilization and precise attitude control. The Astrobee's attitude is very well preserved against the disturbances introduced by the manipulator motion, and the backstepping controller is more flexible and precise, but both the controllers are able to reach and restore the desired orientation in acceptable times, also when an object is gripped. The NASA Astrobee software verified the results obtained despite the synchronization errors. Possible future works are the implementation of the actuators in the mathematical model and the combination of attitude and position control to test the system in a more challenging task. Thank you for the audience.
Okay, sorry about that delay. Very cool stuff. Thanks for all that great information from our presenters. I would now like to bring up George Freas, our session chair. So George, there you are. Looks like you're online and ready. Good, but before I turn it over to you, please remember to submit your questions using the Q&A tool. It's down the bottom of your screen down there. Just click on that, submit your question, and we'll put it to our presenters. So feel free to do that. And with that, George, I'll turn it over to you.
Well, welcome to the 2020 ISSR&D conference. Many thanks to the American Astronautical Society, Jim Way and Alan DeLuna for an awesome conference so far. Also thanks to the panelists for excellent presentations of their interesting research. If you have not already done it, please take time to download the full presentations and view them, because the presentations you just saw are just overviews of the research. So with that, I'll introduce our esteemed panelists. John Williamson works for SAIC in Seattle, Washington. He currently works on the Air Force's Pilot Training Next program. John Kichury works for Hewlett Packard Enterprise in Morris Plains, New Jersey. He is the lead software developer for the spaceborne computer they have on orbit now. Patrick Fink works for NASA in Houston, Texas. Mr. Fink has a BS, MS degrees from the University of Texas, Austin, and a PhD from the University of Houston. Ian Miller works at the University of Pennsylvania in Philadelphia. He's a PhD student there, and he is a 2018 NASA Space Technology Research Fellow. Dario Ruggiero is from Torino, Italy, and is a graduate student of mechanical and aerospace engineering there. So with that, let's see, do we have any questions right now? I have one for Ian. Can Ian explain his presentation in simple language?
I can take a stab at it.
Yeah.
So if you want to survey, imagine you want to survey a like flat surface, like a field or something. How you would do that is relatively clear. You would probably walk back and forth to try to fill up the space of that plane. But when you're in the ISS or in any kind of space environment, there isn't really any down, so to speak. And there's a lot of planes all around you. So you need to decompose or break down the larger environment into a bunch of smaller planar pieces, which you can survey individually and then do those sequentially. That's the high level idea of what we do.
Okay, so here's one also for Ian. How did you get it done so quickly, and what additions, major changes do you plan to do in the full version? Oh, no, this is for John Williamson, excuse me. So how did you get it done so quickly, and what additions, major changes do you plan to do in the full version? Also, what kind of VR equipment will it need to be used later on, say on a regular gaming PC with VR enough, or do you need really high-end equipment?
Thank you. Those are great questions. So a lot of it came from the fact that we do a lot of work in Unity and Unreal, and part of the great things about those two engines now is that they're both free for you to download and experiment with. They're taught at most of the major colleges, including the game colleges that I've taught at, such as Digipen here in Seattle and Harrisburg out there in Pennsylvania. So they're very easy tools to use, and you can get started in them, and there's lots of great online tutorials, but we were able to rapidly iterate just because we're so used to them, and you can actually now go to the asset store and purchase things like the original ISS model that we used to get us going. You just need a gaming PC. You don't need a high-end system anymore. Probably $1,000 will get you what you're after. But one of the more interesting things now is you can actually pivot to the standalone VR devices like the Oculus Quest and Quest 2 in particular. We're actually looking to port those, our system to that, because then it's a completely wireless self-contained system for about $300. I think that answers the majority of the questions, but more than happy to, I could ramble on that for hours. So.
Okay, thank you for your answer. So this is another one for Ian. From the simulation, it seems you used a simplified condition, but in reality, there are cables hanging from the PC and experiment racks. Are you planning to implement them in your simulation, and what would be the difficulties you would face? Wouldn't it be much harder for the robot to move freely in reality than shown in simulation?
Yeah, that's a great question. So there's kind of two answers. The one answer is that we have a wall standoff distance. So typically most of the geometric complexity and clutter is located pretty close to the walls, and if we stay sufficiently far away from it, then we're reasonably safe. The second strategy is we're just generating waypoints. So if I tell the robot that it should go to this position, it's up to the robot to figure out how to get there. And the robot has a much higher fidelity understanding. It has a bunch of active sensors on it and such to tell it about what the obstacles around it are. So it can say, oh, there's a cable between me and where I want to go. I can fly around that. But that's handled by the lower level flight software, whereas I'm just generating waypoints.
Thank you for that answer. The next question is for Dario. Where were you able to determine the mathematical model for attitude control, and was there any latency issue with the software processing power under real or simulation conditions?
Yeah, that's a good question. The mathematical model has been determined just simplifying the actual structure of the Astrobee, and by considering the manipulator non-linked with the main body structure, and then they are linked together in a second way. And by doing that, we can achieve a mathematical model for the overall structure that it's determined through the through the angular momentum conservation. And about the simulation conditions, yeah, they are simplified too in the mathematical simulation, while in the Astrobee simulator, they are simplified too, but the link between Simulink and the simulator makes some latency issue. Yeah, that's true, because it's there is an high computational cost that leads to latency and errors in the simulation results.
Thank you. So I have some questions of my own. John Williamson, I noticed in your presentation you had some future applications. So what is glass ISS see-through docking / remote arm?
So the idea on that one comes from the glass tank ideas and the F-35 cockpit, where using cameras around them, you can actually put on the headset and then look through your tank or look through your airplane. And so in this case, you'd be able to actually look through the ISS and be able to actually see a complete view of, say, the robot arm, as opposed to just the smaller view. You could also then use that to put on the headset and actually look through the ISS and see where the astronauts were, or the actual position of the solar panels, just about anything like that, using combinations. You know, I think some of the other gentlemen presented with the Internet of Things types of integration.
Mm-hmm. Along those lines, also, what is Buck Rogers PR?
Oh, so that was one where basically using virtual reality to give people you know, the experience of going to space in an effort to try to make them more excited about it, to get more tax money spent towards the event.
Yeah.
Yeah. So there's you can, you know, do some of the you know, lower cost you know, low gravity simulation that's enough to get people excited. You know, the one thing I was, you know, also interested in was to try to see if you could begin to get a small taste of the overview effect in VR, because that a lot of astronauts have, you know, responded with how transformative that experience was, and if you could allow people to do that here on Earth, you know, that could be quite an exciting development, I believe.
And also, what is the Overlook Effect?
The Overlook Effect has been reported by several astronauts when they are out in space and they look back and see the Earth and realize, you know, they've reported as being a fairly emotional experience, and the ability to see the Earth in its entirety while you're out there in kind of isolation, they've, you know, reported as being calming, transformative, makes them understand that we're all connected, you know, et cetera. I don't have the exact quotes in front of me anymore, but if you look it up, there's actually some very interesting quotes from people who've been to space.
Mm-hmm. So the last one, it seems like triangulating the positions of the astronauts will be compute intensive.
No, I don't.
In some scenarios, may be problematic. Would not a better approach be using another technology like RF or infrared?
I definitely think a combination of the two could be used. I think it probably actually fits in with some of the work that Ian presented as well. And, you know, there probably aren't enough cameras to actually do it completely, as far as I understand it, but it is a fairly common used procedure that I think we could do, you know, judiciously. But having the IR or the Internet of Things technology on there is a way to actually better track things, I think would be the perfect solution, to combine all of them to take into account when they're out of camera view.
Thank you.
Thank you.
Those are excellent answers. I have a question or two for John Kichury. what security protocols are in place for transmission to from the experiment and the ground, aside from what the HOSC and ISS provide?
That's pretty much what we do is use the NASA network and all the security there to give us a private VPN.
Mm-hmm.
And then on top of that, we do encrypt and compress data to and from our payload.
Okay, so you do have an extra layer of encryption there.
Yeah.
Okay. So what OS runs on the HPC on board?
It was Red Hat, Linux.
Okay. You have good experiences with that?
Yes. Yeah, actually, we were running for almost 2 years and had no system interruptions based on our hardware failures and all that. We had some interruptions because we had a power outage where the way it was explained to us is an astronaut fell up and his knee hit the emergency power cutoff, so that took the power down. Things like that, but the system stayed functional all during that time.
Excellent, thank you. Another one for Ian. What is the source of the funding of your project, and are there plans to deploy this for testing on ISS?
It's a NASA Space Technology Research Fellowship. And yes, so you may or may not have heard of the ISSC project, which has to do with improving like sort of autonomous system awareness for things like the Lunar Gateway, which are going to be uncrewed for long periods of time. And so the first demo for ISSC has to do with mapping. So we're hoping to use this surveying tool in order to generate trajectories for that demo.
Excellent, thank you. And then Dario, the same question, what source of funding do you have, and do you have plans to deploy this to the ISS?
Excuse me, can you repeat the question?
What is the source of the funding for the project, and are there plans to deploy this for testing on the ISS?
Yeah, there aren't funds on this project since it's a project born to my personal thesis work to get my graduation. And there are actually this research that aims to a bigger project where more challenging tasks can be executed and tested between more robots. And so it's just the first point for bigger research.
Okay, thank you. Now, there's another question here for John Williamson. How much time lag would be involved between the EDA crew and the ground controller?
For actually doing the computations inside the VR system, it should be negligible, measured in just milliseconds. So it should just be exactly what the system currently has in it, which as an outsider, I probably couldn't answer, but I imagine it's just a few seconds. But I think somebody else could probably answer that one better than I.
Okay, and now for Dr. Fink. I'm curious about the application of machine learning on your project. So there's two questions. Is the purpose of machine learning to predict the location of lost items or items astronauts are looking for? And the second question, do the algorithms consider last known locations and weight those racks modules more heavily?
Yeah, so the answer to the first question, that it is designed, one of the functions that was designed in is to find lost items. And so the machine learning algorithms that we've been using to date so far tend to use about an hour of data to inform a decision. We are working on some that respond more real time, but we haven't proceeded too far with those yet. I'm sorry, the second question again, please.
Do the algorithms consider last known locations and weight those racks / modules more heavily?
No, not yet. We've kind of slowly moved from full human in the loop and starting to rely and get, depend more on the algorithms. So in occasion we'll throw human back in the loop to as an arbiter between multiple algorithms, and in that case we do look at last known locations. But we haven't weighted the algorithms with that data yet.
Excellent, thank you.
Sure.
I have one for Mr. Kichury. Your dashboard appears real time or near real time. What is the latency there? What was the most useful thing you saw on the dashboard that alerted you to a possible system problem?
Well, the actual latency for the updates can happen every few seconds to many seconds, depending on, as you know, there are a lot of LOS periods, so we couldn't do anything about that unless we ran a cable directly to the ISS. So, and then probably the most interesting thing, the informative thing, is just have the dashboard there, and every time an anomaly crept up, we did have a power inverter fail that NASA provided. We were running these systems. These were just standard off-the-shelf systems with AC power supplies. So NASA provided inverters, go DC to AC for us to run. And we had a failure on one of those, and then the dashboard would immediately tell us when things happened. So that was really informative.
I have a couple questions for you too. Is this going to be like a commercial product that other payload developers could use?
I don't know what the company has in store for the whole software stack. This was really specifically developed to run the payloads to test out HPC in space. So we didn't know if these systems would even function. And so everything was custom built for this specific workload. Now, we have Spaceborne Computer 2, which is being designed and built now. We've enhanced a lot of the functions in the dashboard, and to allow a little more flexibility, so we can have arbitrary applications added to the workload, and we can rearrange things and control the workflow in the experiments. But I don't know that it'll become a commercially available set of software.
Okay, thank you. Here's a question for Ian. Are you thinking to add any more features into your project after completing the mapping?
Kind of. So what I'm currently looking at is a sort of general research field known as semantic mapping, where instead of building a map representation, which is sort of fundamentally geometric in nature, like where is there obstacle, where is there not obstacle, we'd like to be able to represent the environment in a way that's more human-like. Like, there's a laptop over here, there's a bag over here, there's an astronaut here, handrail here. And so we're interested in algorithms that can map the interior of the ISS using that kind of a representation, as well as localizing Astrobee. So a problem recently is like the Astrobee currently uses a feature-based, low-level image feature-based localization system, which doesn't do very well when there's lighting changes or other significant environmental changes. So we're hoping that instead of saying there's like an edge here or a corner here, we can say there's a laptop to my left and a laptop behind me and a handrail above me. That means I'm here. So somewhat related, but not quite the same project per se.
Excellent, thank you. Now for Dr. Fink again, how are you measuring the change in the ability to find an item?
Good question. Our primary metric right now is RMS error, and what we're using as the truth is the data set from the current inventory management system. which is updated mostly on the ground, and you know, movements in that are reported by the crew. So it is considered a noisy data set. And then there's also the question is we've got two different types of algorithms. The regressors give back, you know, X, Y, Z coordinates, and the classifiers, you know, classified to a rack. And so when a classifier estimates the correct rack, then we assign that an error of 50 centimeters. Otherwise, we compute the Euclidean distance from the missed rack. But that's our primary method right now. We're looking at, as shown, I think, in the graph in the full presentation, curves of the RMS error as a function of the tag population percentile.
Thank you. For Mr. Kichury, what is the configuration for the PC, and is there any shielding?
Did you say PC?
Yeah,
Yeah.
well, your HPC.
Yeah. Okay. So, no, we didn't have any special shielding. These are just standard off-the-shelf 1U servers. We had two of them in a locker or an enclosure to fit in the rack. And the only additional shielding, if you want to call it that, is just the metal that the locker was made out of. And that was the whole idea, to see if we would run into issues. And we did have some bit flips in the L3 cache memory in the CPUs, but nothing caused the system to come down. And which was a surprise. All of us, you know, you hear stories, these things are going to fail because of radiation, and it ran pretty well.
There are some components that are naturally rad resistant. But the technology in your PC is just standard CMOS or?
Yes.
Yeah.
Yep. They were the 1U 2-socket servers. We had two of those clustered together, and then and they were both running. And like I said, we did have SSDs fail, and the system the OS disks didn't. System stayed functional, but we were running a whole series of tests, HPC workloads, to really exercise the CPU memory and everything. And then we had a series of SSDs in there, and we were periodically just doing a lot of IOs to them to see what would happen. And we've had several of them fail permanently. And all of those anomalies, if you look at my full presentation, I have a track viewer that plots where things happen, and we try to correlate those times. We fed those back to NASA and try to correlate those to known events, whether it be solar flares or whatever, and they just said it was GCR caused the bit flips, and so we attributed to that.
Thank you very much. Mr. Williamson, can we play with the VR software in person after COVID? This is a person at Franklin High School in El Paso, Texas.
I actually, one of the many high schools I went to, and the one I ended up graduating from was actually there in El Paso. We can't quite give away mine, but there are some amazing virtual reality apps out there. I actually have an entire lecture about them. The one most interesting one I find for most people is the Apollo 11 experience. So you actually get to circle the launch vehicle. You actually get to go into space. You actually try to dock the two components after they separate. I'm gonna get the acronyms wrong, so I won't say them. And then actually spend a little bit of time with the astronauts as they make the journey, and then actually end up on the moon. That runs on most VR systems. It's an amazing experience. But contact me afterwards, and I can send you a link of other space software that I think is perfect for use in educational environments. Thank you.
Thank you. Here's one for Ian again. What software are you using for mapping?
So I didn't do, at least for what I presented here, I wasn't directly involved with the mapping side of things. I was involved with the planning to map side of things. But the mapping tool that is being used is one that's been developed in-house. by names. But it's not like the main method is like structure for motion. So basically you take a bunch of images, and the robot has a decent idea of where those images are taken from, and so then you can project those images back onto the geometry that you know exists, and then you can do a basically kind of like your phone does when you take a panorama. You can then basically align those images nicely. So it's not like a free tool that's out there, but those are the ideas that are behind it.
Excellent, thank you. Let's see. Okay, for Mr. Williamson, could EVA crew also use your VR system in the near future?
Are we talking about the astronauts themselves who are out doing the EVA? I know that NASA currently is working on designing the next EVA system with trying to design a HUD that can go inside the helmet as well. And so I definitely think you could put some of that in there to not only show them what the other astronauts were doing, but again bring up that information and display instructions or a video feed and do that. They've actually demonstrated some of that inside the ISS with the Microsoft HoloLens, because on that one you see down in Houston, you see exactly what the astronauts seen from their perspective, and you can draw on top of that and say, no, it's not that nut over there that you need to adjust, it's this one right here, and actually draw a circle around it to eliminate any of that confusion that you might have trying to navigate 3D space, especially if it's something that doesn't happen very often. So it could significantly reduce some of the training. Instead of having to train for all of the possible contingencies, train for a smaller subset, and if one of the things are least likely to happen, then you can actually do that live and feedback there from Earth. So yes, I do think it could be used by the EVA crew once the new headset designs are complete.
Fascinating, thank you. So do any of you panelists have questions of other panelists? We have about 5 minutes left. So
I had another question for Dr. Fink about the machine learning side of things. How do you supervise the model? Do you assume ground truth locations for things? Is this trained in simulation or on the ISS?
Yeah, that's a great question. That's been one of our biggest challenges, is getting enough real truth data on the vehicle. The whole premise of this is to learn how to do autonomous logistics management for deep space exploration, but at the same time, we also want to help improve efficiencies on the space station. So we try to minimize, asking the crew to go check locations of items for truth, to improve our truth data. So we do rely on that, and it's a noisy data source. It depending on who you ask, you get different estimates on what the accuracy of that database is without any RFID supplementing information. On the low end, it's probably 90%. And so we do also have about 100 marker tags. They're fixed RFID tags on the structure. It's really insufficient to serve as a complete training set, in part because attaching the tags to the structure requires a different type of tag than what you put on the cargo, because most of the cargo tags are for non-metal and the structure, of course, is metal. so it responds a little bit differently. And then in addition, it's not representative of the tags that are on cargo. They're put into stowage volume. So it's a little bit different. We find that it's not in and of itself a complete, sufficient training or training set. So our main method of building confidence in what we're doing is we also have an analog on the ground. It's a cylindrical single module. It tends to be a little smaller than space station. It's about 3 meter diameter and 6 meter long. Happens to be fairly close to the current Gateway Halo design, so it is giving us some insight into that. But for the most part, we're seeing a pretty good confirmation that the results we're getting on space station, we can do, replicate those in our ground analog. So that, and of course, obviously, we have a whole lot more control over the training data on the ground.
Thank you. There's one here for Mr. Williamson. Again, it's very similar to the last one. Can the VR project be integrated in the astronaut suit to help doing their mission outside? And
Yeah, again, I think on the new designs to actually include a HUD inside the helmet, you know, I think that could be done. Depending upon what they ended up doing there. There's a lot of challenges there, you know, regarding the high oxygen and inside the headset and the electric requirements, but I believe it definitely would be very possible. The Navy for a while had a HUD actually put inside their diving helmets. So I think that is actually a good place to start. And again, using a lot of the video game head technologies that are out there as inspiration. And actually, Microsoft on the HoloLens 2, one of their largest contracts is essentially actually using the HoloLens to display that type of information for Armed Special Forces units. So there's definitely a lot of groups working towards that. And again, the helmet inside the F-35 carries a lot of HUD displays inside of the helmet itself. So yes, short answer, yes.
okay, here's a question about the RFID technology. Is it being used for COVID tracing in your company or any others? Since you work for NASA.
Yeah, that's a great question. It's my understanding that it is being used in certain areas. No, I don't think so much that I know of for contact tracing. I think more for equipment and supplies. I think the big challenge with RFID for that application is just the range. It's, you know, the typical rule of thumb is about 30 foot of range. So it could do quite well in a very close environment with, you know, workers close by, but then you'd have to translate and hand off to something else as distances start to increase.
All right. Hey, George, it's Jim Way. I'm just jumping in here. Think we're good?
To the end.
Great. Hey, everybody, that was fantastic. That was really cool stuff. So thank you very much to everybody for this one. Just love the content here. That was amazing. So with that, yes, thank you again, George, all of our panelists. We really appreciate your doing this. And so right now, we're going to take a bit of a break. So we will be breaking until noon Eastern, 1600 Universal, when we'll come right back right here in this same Zoom room for our next panel on advanced materials and manufacturing. So take a look at that, get your questions ready, and we'll see you in about 45 minutes. Thanks, everybody.